Any object in our world has its own expected life cycle. This lifespan may be comparatively short for some objects, while others will be around forever almost literally. In comparison with the life expectancy of these objects, an average human life seems to pass in the blink of an eye. But what will the autumn years of such objects as stars look like? And will we ever be able to observe what a dying star is like? Will mankind ever see the so-called black dwarf? The term stellar evolution in astronomy refers to the sequence of changes that a star undergoes throughout its entire life. This process largely depends on the object's initial mass, and may take anything from several million to tens of billions of years. As a rule, a star originates from a cloud of cold, low-pressure interstellar gas. Due to gravitational instability, the cloud compresses and eventually slowly assumes a spherical shape. During the compression process, the gravitational field energy is transformed into heat and radiation, with the temperature of the young star gradually going up. The duration of this stage depends directly on the star's initial mass. With the heaviest stars, it may take about 100,000 years, and with the lightest ones, the phase may last up to several billion years. Our Sun's mass, for instance, is comparatively small, and so it remained in this first phase for approximately 110 million years. In the next phase, after a sufficiently high temperature has been reached at the core, thermonuclear fusion takes place inside the star and the compression ceases. After this, the processes taking place at the core become the star's only energy source, and thus a young star, which is also called a protostar, becomes a main sequence star. This is the starting point for calculating a star's age, as this phase accounts for approximately 90% of its life cycle. Our Sun, for example, will remain in the main sequence stage for approximately 11.5 billion years. When a star enters its main sequence stage, its chemical composition is still very close to interstellar environment and is 91% hydrogen. At the same time, the process of hydrogen transforming into helium is constantly in progress inside the star. As a result, the core compresses and gains in density, which gradually increases the rate of chemical reactions. It leads to noticeable changes in the star's properties. For example, the luminosity of our Sun in the main sequence stage accounted for only 70% of its luminosity today. By the time this stage is over, the luminosity is going to be 2.2 times that of today. It should be mentioned that not all stars make it to the main sequence stage. The exceptions known to science today are referred to as cold and hot subdwarfs. These objects are very similar to main sequence stars, but they do differ from them. Thus, by contrast, subdwarfs are not rich in heavy elements and are not so luminous. The final phase for main sequence stars also depends on their mass. Generally, a star either discards its outer coat, thus becoming a white dwarf, or goes supernova to later become a neutron star or a black hole. A supernova is a phenomenon when a star's luminosity dramatically intensifies, with great amounts of energy released during the process. After that, the flare slowly fades. This explosion is accompanied by emissions of great amounts of matter from the outer coat. The remaining matter in the core of the star gone supernova generally forms a compact object, either a neutron star or a black hole. Apart from everything else, the matter released in the course of a supernova event contains products of thermonuclear synthesis. It is thanks to these elements that the universe is able to evolutionize chemistry-wise. If a star's mass doesn't quite reach 8 sun masses, however, this main sequence star will end up being a white dwarf. That is, an object which is a hot celestial body of small dimensions and a high density. For instance, in the case with our Sun, when the time comes for it to go through this phase, it is going to become 100 times smaller than it is now. White dwarfs do not generate energy and are luminous only on account of their high temperature. Even though the hottest white dwarf's surfaces may be as scorching as 70,000 kelvins, due to their small size, their luminosity is not that great. As for their average density, it is almost 1,000,000 times that of the regular density of main sequence stars. These objects consist for the most part of a plasma of nuclei and electrons, and are completely devoid of thermonuclear energy sources, which is why they gradually cool off and assume a red hue. Sirius B is the closest white dwarf to us that we currently know of, and it is 8.6 light-years away. This object's mass is give or take that of the Sun, and is considered to be one of the most massive white dwarfs known today. Its volume is 1/1,000,000th of that of the Sun, and its dimensions are identical to those of our Earth. Sirius B is believed to have become a white dwarf approximately 120 million years ago, with the initial mass of the star in its main sequence phase having been 5 Sun masses. Today, it is posited that these objects account for 3 to 10% of the overall stellar population of our galaxy according to different estimates. Over 97% of the stars known today are eventually destined to become white dwarfs. As time goes by, these objects are bound to cool off and fade. Eventually, all celestial bodies of this variety will become black dwarfs, which implies that they will completely cease to emit any visible light. This process takes scores of billions of years. That is why to date science hasn't had a chance to observe any of these objects. The universe is considered to be too young to have produced any black dwarfs at this point, but scientists have already managed to spot objects quite similar to them, whose temperature has gone down lower than 4,000 kelvins. These objects are white dwarfs WD0346+246 and SDSS J110-217. A black dwarf is what most stars look like at the final stage of their evolution. Its mass is quite identical to that of a white dwarf. According to today's models demonstrating cooling of these bodies, white dwarfs formed in the course of the evolution of the first generation of stars are supposed to have a temperature of approximately 3,200 kelvins and to appear as rather dim objects. For all we know, these celestial bodies could be part of the universe's hidden mass components. For a white dwarf to cool off to the temperature as low as 5 kelvins, it may take approximately 1 quadrillion years. In theory, when black dwarfs cool off completely, the process of dark matter annihilation becomes very important for their existence. This phenomenon hasn't been directly observed in the universe yet, although it is thought that in the course of annihilation, particles of dark matter will form ordinary photons and emit light visible through a telescope. Without allowing for this phenomenon, black dwarfs are believed to cool off and fade to the point where their temperature equals the background temperature of the universe. However, in theory, thanks to the energy derived from dark matter annihilation, black dwarfs may well continue to radiate energy for a considerably longer period, and thus enjoy their luminosity longer. The process of dark matter annihilation in these objects is thought to continue for as long as the galactic halo remains whole, and that means for over a septillion years. After that, dark matter annihilation gradually ceases, and only then will black dwarfs cool off completely. It is likely that mankind will never be able to discover objects of this kind, as the main period of their life takes place in the phase in the life of our universe which will come after the one we're in at the moment. The period we live in is a star epoch. That is the period where stars are still born quite actively. This epoch will last up until the point when the galaxies will deplete all of their interstellar gas. After that, it will be the turn of low-mass stars like our Sun to fade. Following that, a long period of disintegration will begin, when white, brown and black dwarfs are the main objects populating the universe. At the next stage, the epoch of black holes, all matter in the universe will be transformed into elementary or subatomic particles, with the remaining black dwarfs getting sucked in by black holes or completely disintegrating. The final stage in the life of the universe is supposed to be the epoch of eternal darkness, where there won't be any energy sources whatsoever in space. The overall temperature in the universe will reach absolute zero. Space will gradually expand, and in the light of the last and rare black holes, in about 1 Google years, our world will come to its gloomy end. By that time, all traces of what was once the human civilization would have become nothing. However, if we can influence the process of the universe's evolution in any way, the course of its life may be significantly altered. Meanwhile, as you watch the Cosmo channel, you motivate me to tell you all about it, as mankind keeps taking a keen interest in prospects for the future. And this means that even after such an unthinkably long time, there is a chance for us to leave our mark in the infinite expanses of our universe.